The question is whether a 20 amp breaker can handle a load consisting of a television drawing 250 watts, a microwave drawing 1450 watts, a microfridge drawing 300 watts, a coffee maker drawing 850 watts, 3 lamps drawing 180 watts, and an iron drawing 1100 watts, totaling 4130 watts, assuming a 0.8 power factor. No, a 20 amp breaker cannot handle this load. Firstly, let's calculate the apparent power. Apparent power, often denoted as S, is equal to the actual power, denoted as P, divided by the power factor, denoted as PF. In this case, the actual power is 4130 watts and the power factor is 0.8. Therefore, the apparent power S equals 4130 watts divided by 0.8, which equals 5162.5 volt amps. Secondly, we need to consider the National Electrical Code, or NEC, requirements. The NEC dictates that a breaker should not be loaded continuously above 80% of its rated capacity. For a 20 amp breaker, the maximum continuous load is 80% of 20 amps, which equals 16 amps. Thirdly, let's convert the apparent power to amps. The apparent power of 5162.5 volt amps corresponds to a current draw of 5162.5 volt amps divided by 120 volts, which equals approximately 43.2 amps. Finally, let's compare the calculated current draw with the NEC limit. The calculated current draw of 43.2 amps significantly exceeds the maximum continuous load of 16 amps allowed for a 20 amp breaker. Therefore, based on NEC requirements and the expected loads, a 20 amp breaker cannot safely handle the simultaneous operation of all the listed devices. A higher rated breaker, such as a 30 amp or 40 amp breaker, would be required to provide adequate protection and prevent circuit overloads. It is crucial to adhere to the NEC guidelines to ensure electrical safety and prevent hazards. Overloading a circuit breaker can lead to overheating, which can damage the wiring and potentially cause a fire. The NEC 80% rule is in place to account for continuous loads, which are defined as loads that operate for 3 hours or more at a time. Continuous loads generate heat in the circuit breaker and wiring, and the 80% rule helps to prevent overheating. In this scenario, it's highly likely that several of the listed devices, such as the microfridge, lamps, and possibly the television, could operate continuously for extended periods. In addition to the 80% rule, the NEC also specifies that the overcurrent protection device, such as the circuit breaker, must be sized to protect the conductors in the circuit. The conductors must be rated to carry the load without overheating. The appropriate wire gauge for a circuit depends on the amperage rating of the circuit breaker. For example, a 20 amp circuit typically requires 12 American wire gauge, or AUG, copper wire. If the load exceeds the ampacity of the wire can overheat and create a fire hazard. Moreover, it is important to consider voltage drop in the circuit. Voltage drop occurs when the voltage at the end of a circuit is lower than the voltage at the beginning of the circuit. Excessive voltage drop can cause appliances to malfunction or operate inefficiently. Voltage drop is affected by the length of the circuit, the wire gauge, and the amount of current flowing through the circuit. The NEC recommends limiting voltage drop to a maximum of 5% for branch circuits and feeders. To mitigate voltage drop, use a larger wire gauge or shorten the length of the circuit. Furthermore, the power factor of the load can affect the current draw on the circuit. Power factor is a measure of how effectively electrical power is being used. A power factor of 1.0 indicates that all of the electrical power is being used to perform work, while a power factor of less than 1.0 indicates that some of the electrical power is being wasted. Inductive loads, such as motors and transformers, typically have a power factor of less than 1.0. The lower the power factor, the higher the current draw on the circuit for a given amount of power. In this scenario, a power factor of 0.8 was assumed. If the actual power factor is lower than 0.8, the current draw on the circuit would be even higher. It is also worth noting that the NEC requires that all electrical work be performed by qualified individuals. Electrical work can be dangerous, and it is important to have the necessary knowledge and skills to perform the work safely. Improper electrical work can lead to electrical shock, fire, and other hazards. When designing an electrical circuit, it is essential to accurately calculate the expected load. This calculation should take into account all of the devices that will be connected to the circuit, as well as the power factor of the load. It is also important to consider the potential for future load growth. If it is anticipated that the load on the circuit will increase in the future, it is best to size the circuit breaker and wiring accordingly. To determine the appropriate breaker size, one must calculate the total load in volt amps. This is done by summing the volt amps of each individual device. The volt amps of a device can be calculated by multiplying the voltage by the current. If the voltage and current are not known, the volt amps can be estimated by dividing the wattage by the power factor. Once the total load in volt amps has been calculated, the required breaker size can be determined. The breaker size should be large enough to handle the total load, but it should not be so large that it exceeds the ampacity of the wiring. The ampacity of the wiring is the maximum amount of current that the wiring can safely carry. The ampacity of wiring is determined by the wire gauge and the type of insulation. The NEC provides tables that list the ampacity of various types of wiring. In summary, several factors must be considered when determining whether a 20 amp breaker can handle a particular load. These factors include the total wattage of the load, the power factor of the load, the NEC 80% rule, the ampacity of the wiring, and the potential for voltage drop. By carefully considering these factors, one can ensure that the electrical circuit is safe and reliable. Considering diversity is another approach. Diversity refers to the probability that all loads will not be operating simultaneously at their maximum rated power. In residential applications, it's common to apply a diversity factor, recognizing that occupants rarely use all appliances at full capacity at the same time. However, applying a diversity factor requires careful engineering judgment and knowledge of the specific usage patterns. It's generally not advisable to rely heavily on diversity factors for critical safety systems or where predictable loads are involved. The given scenario involves a hotel room where usage patterns can be unpredictable and potentially high, especially during peak seasons. Therefore, relying on diversity alone to justify overloading a 20 amp breaker would be imprudent. Instead, the design should prioritize safety and code compliance by ensuring the breaker is adequately sized for the potential load. The calculation provided uses a power factor of 0.8. Power factor represents the ratio of real power watts to apparent power volt amps. A lower power factor indicates a less efficient use of electrical power, resulting in higher current draw for the same amount of real power. Many electronic devices, especially those with motors or transformers, have power factors less than 1.0. If the actual power factor of the connected loads is lower than 0.8, the current draw will be higher, further increasing the risk of overloading the breaker. It's crucial to consider the power factor when calculating the total load on a circuit to ensure accurate sizing of the breaker and wiring. The NEC specifies requirements for overcurrent protection to protect conductors and equipment from damage due to excessive current flow. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. This prevents overheating of conductors and equipment, reducing the risk of fire or damage. Circuit breakers are resettable, meaning they can be manually reset after tripping due to an overload or short circuit. Fuses, on the other hand, are single-use devices that must be replaced after they blow. The NEC outlines specific requirements for the selection and installation of overcurrent protection devices, including ampacity ratings, interrupting ratings, and coordination with other protective devices in the system. Proper overcurrent protection is essential for ensuring the safety and reliability of electrical systems. The NEC provides guidelines for determining the appropriate conductor size for electrical circuits based on the ampacity of the conductors. Conductor ampacity is the maximum current a conductor can carry continuously under specified conditions without exceeding its temperature rating. The NEC specifies ampacity tables for various types of conductors based on their insulation type, temperature rating, and installation method. When selecting conductors for a circuit, it's essential to choose a conductor size with an ampacity equal to or greater than the calculated load current. In addition to ampacity, conductors must also be suitable for the voltage and environmental conditions of the installation. The NEC provides detailed requirements for conductor selection to ensure safe and reliable operation of electrical systems. The NEC also addresses the requirements for grounding and bonding of electrical systems. Grounding provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to quickly interrupt the circuit and prevent electrical shock hazards. Bonding ensures that all metal parts of an electrical system are electrically connected, minimizing voltage differences and reducing the risk of electric shock. The NEC specifies detailed requirements for grounding electrodes, grounding conductors, bonding jumpers, and other components of grounding and bonding systems. Proper grounding and bonding are essential for protecting people and equipment from electrical hazards. The NEC outlines specific requirements for branch circuits, which are the circuits that supply power to individual loads or outlets. Branch circuits are classified based on their voltage and amperage rating, such as 120 volt 15 amp branch circuits or 240 volt 30 amp branch circuits. The NEC specifies the types of loads that can be connected to each type of branch circuit, as well as the requirements for overcurrent protection, conductor size, and wiring methods. Branch circuits must be designed and installed in accordance with the NEC to ensure safe and reliable operation. The video should also mention the importance of consulting with a qualified electrician for any electrical work. Electrical work can be dangerous, and it's essential to have the necessary knowledge and skills to perform the work safely. A qualified electrician can assess the electrical system, determine the appropriate breaker size and wiring, and ensure that all work is performed in accordance with the NEC and local codes. Attempting to perform electrical work without proper training and experience can lead to electrical shock, fire, and other hazards. The hotel room design needs to comply with all applicable electrical codes, including the NEC and any local amendments. Codes are in place to ensure the safety of people and property, and they must be followed rigorously. Ignoring code requirements can result in serious consequences, including fines, legal liability, and potential harm to occupants. It's essential to stay up to date with the latest code requirements and to consult with a qualified electrician or electrical engineer to ensure compliance. A load calculation is a systematic process of determining the total electrical demand of a building or electrical system. Load calculations are essential for sizing service entrances, feeders, branch circuits, and overcurrent protection devices. The NEC provides detailed guidelines for performing load calculations, taking into account factors such as lighting, receptacle outlets, appliances, motors, and heating and cooling equipment. Accurate load calculations are critical for ensuring that the electrical system has sufficient capacity to meet the demands of the building or system without overloading. When performing load calculations, it's important to consider both the connected load and the demand factor. The connected load is the total wattage or volt-amperes of all the electrical equipment connected to a circuit or system. The demand factor is a multiplier that accounts for the fact that not all of the connected loads will be operating simultaneously at their maximum capacity. Demand factors vary depending on the type of load and the occupancy of the building. The NEC provides demand factors for various types of loads, and it's important to use the appropriate demand factors to avoid oversizing or undersizing the electrical system. The video could also discuss the concept of arc fault circuit interrupters, or SICs. SICs are a type of circuit breaker that is designed to protect against arc faults, which are dangerous electrical conditions that can cause fires. Arc faults occur where electricity jumps between two conductors, creating a spark that can ignite nearby flammable materials. SICs detect arc faults by monitoring the current waveform and tripping the circuit breaker when an arc fault is detected. The NEC requires SICs to be installed in certain locations, such as bedrooms and living rooms, to protect against arc fault hazards. Finally, it's important to regularly inspect and maintain electrical systems to ensure their continued safety and reliability. Electrical systems should be inspected periodically for signs of damage, wear, or corrosion. Any problems should be addressed promptly to prevent further damage or potential hazards. Regular maintenance, such as tightening connections and cleaning components, can help to extend the life of the electrical system and prevent breakdowns. By following these recommendations, the design can be made safer and more compliant with electrical standards and best practices. The original question presents a scenario commonly encountered in electrical design where multiple loads are expected to be used on a single circuit. It's essential to remember that electrical safety should always be the top priority. Overloading circuits can lead to dangerous situations and should be avoided.